Hello, and welcome back to the Maths Behind the Economics YouTube channel. This is video 14 in the Logs for Economics series, and in this video, we're going to explore when logs cancel down to 1. As always, I'm going to show you the rule, then we'll discuss why the rule works and we also prove it formally, and towards the end of the video, we're going to look at plenty of examples. Let us get going. Here is the rule in both forms, the generic and the special case of ln. So let us spend a couple of minutes on trying to understand how the rule works. First of all, what we observe is that there are two logs that are multiplied together. However, they have got different bases. And furthermore, what's the base in one of them? For example, the first have got base b, then that becomes the argument of the second log. And what was the argument of the first log becomes the base of the second log. So basically, once you multiply two logs together where the role of the base and the argument is switched around, they will cancel down each other into 1. Okay? The special case of this would be ln of x times log base xe being equal to 1. Next, let us look at some examples and see how this rule works with specific log bases and arguments. So for example, if I have got log base 2, 5 and I multiply this by log base 5, 2, what am I gonna end up with? Well, first of all, I've noticed that I've got two different bases in the two logs. So I should make both logs the same base. And for that, I'm going to use the rule, the change of base rule that we learned in video 12. And I'm going to leave the first base alone, so I'm going to leave log base 2, 5 unchanged. But now what I'm going to do, I'm going to rewrite log base 5, 2 as log base 2. So I need to write down log base 2 over log base 2. And then what goes at the top? Old argument. And at the bottom goes the old base. Now, what have we got here? Well, I'm multiplying by log 2, 5, and at the same time, I'm dividing by log 2, 5. So log 2, 5 cancels out log 2, 5 in here. What I ended up with is log base 2, 2. But hold on, that is just equal to 1, as we discussed in details in video 5 of the log series. Okay, this is lovely. Because if we have got the specific base of 2 and argument 5, which then gets switched into base 5 and argument 2, the rule holds. Okay, that's just one example. Let's look at a slightly different example. So if I have LOGE and I multiply that by ln 10, what's happening in here? Well, LOG in mathematics is base 10. And ln in mathematics is base e. So what I notice is that this multiple follows the same logic. I switch the base and the argument of the first log in the second log. Okay, so what are we gonna do? Well, we're gonna have to make both terms of the multiplication having the same base. And because this is a video about economics, we're going to choose ln to be the common base. So we're gonna rewrite LOGE in terms of ln. It's going to be ln of e over ln of 10. Remember, e is the argument and the base is 10 in the original LOGE. Now I have to multiply this with ln 10, and just like in the previous example, ln 10 will cancel out ln 10, and what I end up with is ln of e. And again, just the same as in the previous example, this is going to be equal to 1 because if the argument and the base is equal to the same number, that log always cancels down to 1, just as we discussed in details in video 5. I think we are now pretty convinced that this rule holds, however, we haven't proved it yet. So let's make a bit more space and start proving why this rule works for every single argument and every single base. Now, first of all, we have to lay the ground rules. Remember, you cannot use specific numbers as base or argument of a logarithm. If you've forgotten this, please check out video 2. So, as always, we're going to have to start with those restrictions. So, let x and b both be a positive number. Remember that in the rule, b was the base in the first term and x was the argument in the first term, which means neither the base nor the argument can be 0 or negative. But on top of that, b as the base cannot be equal to 1. Now, in the second term in the rule, we switched the rows of x and b. In the second term in the multiplication, x has become the base, but that means now that x itself can't be equal to 1 either, because if we have got a log base of 1, that is not really a log. And here I again refer to video 2, in which we discussed in details why the base cannot be equal to 1. Now that we understand what numbers can be our bases and arguments, then we claim that log bx multiplied by log xb is going to be equal to 1. Well, what we're going to do here is we're going to use the change of base rule again. So I can write here by change of base. And then what we're going to do, we're going to leave the first log unchanged and we're going to rewrite the second log as a base of b. So what we need here is log base bb all over log base bx. Now, what we got here? Well, we got here that log bx is multiplying and dividing at the same time. So, multiplying by the same number and dividing by the same number, that just cancels down to 1. And 1 times anything will just give you that anything. So, what I'm going to end up with is log bb. But now, by the definition of the log, and I can write here by log def, which means by the definition of the log, I can replace log bb by 1. Again, why? Remember, any number raised to the first exponent power is always equal to the number itself. And what are logs? Logs are powers. So if I was to rewrite this in a log form, I could write log base a equals to 1. Now, this proof was again one of the shorter ones. And if you look at the steps in the proof, we basically just applied the change of base formula. So this equality is an application of the change of base rule from video 12. So let us make a little bit more space and then start to do some practice questions. Question number 1 is going to be log base 5 times log base 3. Well, this is just a direct application of the rule. Why? Well, we recognize that the base of the first log in the multiplication is the argument of the second log in the multiplication. And furthermore, the argument of the first log is the base of the second log. So we can just replace this whole expression by 1. Wasn't that nice and easy? Let's up our game and do something a little bit more challenging. So let's do log base 325 times log base 9. Well, what's happening in here? The argument in the first log, the 25, is the square of the 5, and the argument of the second log, the 9, is the square of 3, which is the base of the first log. So if we rewrite these two arguments in power forms, we might be able to spot the rule a little bit easier. So log base 5 squared times log base 3 squared. Now we're almost there. We can almost apply the rule, except for there are exponents in both logs. So what we need to do, bring those exponents down. So we can write 2 times log base 5 times 2 log base 3. And now because these two numbers are multipliers, and remember, if there's nothing in between a number and an expression or a letter, that's always multiplication. And also because we can change the order of multiplication without changing the final result, I can rewrite this whole thing as 2 times log base 5 times log base 3. And now, in this term, this is just our rule. So this whole thing can be replaced by 1, because remember, The base of the first log now is the argument of the second log, and the argument of the first log is the base of the second log. So this whole expression is just equals to 4. What a cheeky little number 4, hiding behind these complicated looking logs. Question number 3. I've got log a squared b cubed times log b cubed a to the 5th. Wow. We can see that a and b are in the argument and in the base, switching rows in the two different log expressions. However, there are all these exponents flying all over the place. So I suggest that first we tame this down a little bit and remove all those exponents. So in the first step, I'm going to bring down these two exponents from behind the log sign. So that's going to be 3 times log base a squared b times 5 log b cubed a. And what I'm also going to do here is collect the number multipliers or coefficients to the front. 3 times 5 going to make 15. And now I've just got log a squared b times log b cubed a. Again, make a bit more space and carry on with our calculation. What we also got here is exponents in the base. So I can't really apply my rules straight away because I don't have a squared in the second argument and I don't have b cubed in the first argument. So what I should do, I should remove the exponents from the bases. And to do that, we just have to apply the rule that we learned in the previous video, in video number 13. So if you have watched video number 13, then you remember that the exponent from the base can be brought out as 1 over multiplier, and then we're just gonna keep the base without the exponent. So the 2 comes out as a 1 over 2 multiplier, and the 3 comes out as a 1 over 3 multiplier from the second log expression. Now, I still have got loads of numbers flying around, so let me collect them together into just one number. 15 times a half times a third is just going to be 15 over 6 because 2 times 3 makes it 6. And what I've got now, I've got log AB times log BA. And voila, I can now replace this with a 1 because our rule says that if you have a multiple of 2 logs in which the role of the argument and the base switches from the first term to the second term, they will just cancel down to 1. So again, 15 over 6, hiding behind this complicated looking logarithmic expression. How about that for a disguise? Fourth practice question. ln 100 times LOGE squared. Okay, so first of all, what I've noticed is that 100 is 10 squared. So I'm going to replace that ln 10 squared times LOGE squared. Now I have got exponents in both expressions, so I can bring those exponents down. So I can bring down a 2 from the ln 10 squared, and I can bring down the 2 from the log e squared. So what I've got here is now 2 times 2 together makes 4 ln 10 times LOGE. Again, remember that in video 4, we have talked about the different notations and what does ln and log stands for. And from that, and hopefully from all the other videos that you have watched with me, we remember that ln is base e and log is base 10. So again, this is the special case of our rule, and that just cancels down to 1. So the whole expression is going to be equal to 4. This cheeky 4, hiding again in a different disguise now. And now for the last practice question for this video, and I anticipate that I will need more space, so let's scroll our page. The question is going to be logx cubed, cube root of y to the 5, times log y squared x to the 4. Now again, there are exponents all over the place. The first thing I've noticed is that cube root of y to the 5 can be replaced as y to the 5 over 3. Remember, our root is a fractional power. But this also means that I will be able to bring out this 5 over 3 in front of the log sign in the first term. So let us just do that. So 5 over 3 logx cubed y. And I'm going to multiply that by 4 logy squared x. Again, this 4 has come down as a multiplier using the rules from video 10. And now, what we notice is that there are still exponents, but in the base. So we can use the rules from video 13 and bring those exponents from the base of the logarithm into 1 over multipliers. So let's carry on with the solution here at the bottom of the page so we got enough space. First thing I'm going to do, I'm going to collect the numeric multipliers, the 5 over 3 and the 4. We have to multiply them together, so that's going to make 20 over 3 because I've got a whole number I multiply by a fraction. That's the same as multiplying the numerator by the whole number and leaving the denominator unchanged. Next thing I'm going to do, I'm going to bring out those green exponents from the bases. Then the first log term can be rewritten as 1 over 3 log x based y. And then the second term can be written as 1 over 2 log base y x. Now, I still have numeric multipliers. So what I'm going to do is multiply 20 over 3 with 1 over 3 and 1 over 2. When you multiply fractions together, you multiply the numerators, which gives me 20, because 20 times 1 times 1 is 20, and the denominators separately, which is 3 times 3 times 2, so that's 18. And then what I've got left is logxy times logyx. And again, because the base of the first log becomes the argument of the second log, and the argument of the first log becomes the base of the second log, I can cancel this whole thing down to 1. And I end up with basically having 20 over 18 hiding behind this very complicated looking logarithmic expression with all sorts of roots and exponents flying all over the place. Well, as I told you previously, logs are interesting. Logs are fascinating. I hope that you learned something new. And if you remember video 7, there were one more rule, rule 10, when the logs and the exponents were cancelling out, but that rule was actually already covered in video 6. So, we have already covered all the rules and all the different nuances around logs. So, from the next video, we're going to focus on practice questions. And we're going to do 3 videos on mixed mathematical types of questions, and we're going to do 3 videos on log questions where the expressions are more like what they would look like in economics. I hope to see you in the next video. Thank you for watching. Bye.